So let's take a look at this pressure thrust in a little more detail. Here's a piping system where there's an expansion joint. Now, on one end, if I look down the line, I see the back end of a pump. And if I look this way, I see the elbow. Perpendicular to my line of sight, I have back of the pump. I also have this last convolution looking this way. These are the balance out last convolution. Now, the different loads that we're talking about here is T1. That's the axial load in the pipe wall. Some of the load is back here. This bit is not there yet. It's actually pushing on the wall. So it's the effective area minus that inside area. This width here, this outer width here of this annulus, or the outer radius, is the diameter of the effective joint, the effective diameter of this cross section. Not the complete inside diameter, the largest part of the convolution, or the smallest. It's the effective diameter, the effective area of the expansion joint. The load T2 is the inside diameter of the pipe, based on that area. T4 is the load on the supports in either end. That's the effective area of the expansion joint, pushing on the base. Now, in Caesar 2, what we place in our model is this T4 at either end of the expansion joint. Again, the proper way to locate this, if you wish to go that far, is most of the load is back here on these elbows or in the back face, with only a little bit right here on either end of the joint. But in Caesar 2, the program doesn't know what is downstream, so it places this load, the total load, on either end of the joint. Now, if you have tie rods in the model, you'll just load up the tie rods. If you don't put the tie rods in the model, it will open up the joint. Now, just to summarize, these expansion joints are added to your piping system to add flexibility, probably for thermal strain or maybe some anchor motion. Sometimes it's maybe a little bit of alignment issues too, but basically they're used to add flexibility to the piping system. Now, these assemblies do not work in all directions though. You noted earlier that I said that if it's untied, it is designed for axial motion. If it's tied, it's designed for lateral motion, and so on. So as soon as you start to work with different types of hardware to contain pressure thrust, you are reducing flexibility in certain directions. So let's take a look at those different joints in terms of the flexibility that they add. Well, an untied joint provides axial freedom. However, you will be required to have guides and support thrusts throughout the system to carry the pressure thrust and direct the motion. You could use it for lateral and bending if you had very low pressure. A tied joint is very compact and stable, but it can only allow lateral deflection, or it's designed for lateral deflection. You can get other out of it, but that's not the design. When you're looking at a hinge joint, your consideration is on the bending term. If you have just one axis open up, it's a single hinge. If you want both axes, it will be a gimbal joint. You will also probably use some guides in this area to make sure you don't push it in the wrong direction. Untied universal is used only for very low pressure because these are very unstable joints, but you can get both axial and lateral deflection out of them. On a tied universal joint, now we have the pressure control on it, and the center spool piece will be a multiplier on the lateral offset available out of any one of those joints. And on a pressure balance joint, you're getting some axial and lateral freedom out of that, and we're controlling the pressure thrust by throwing an expansion joint outside the limit of the exiting leg. Now, if you're going to be using expansion joints, I would suggest you get familiar with Expansion Joint Manufacturers Association. This is a very small booklet that you can purchase from Expansion Joint Manufacturers Association. Here's the address if you wish. It'll explain the different parts in an expansion joint and how to design a system with expansion joints and proper installation and handling. So when you're selecting a joint, you want to be able to provide flexibility in specific directions. You'll be also concerned about space requirements for the joint and the support requirements for that joint. This graph here was developed by a gentleman at Senior Flexonics Pathway. Dan Edgar was working with Tony Paulin years ago in developing the expansion joint modeler in Caesar 2. And this was the flow chart that he developed with Tony to do a complete model of an expansion joint. They certainly brought back on some of their requirements here, and it didn't get to this level of detail, but you can see there's all different types of joints here. And is it restrained or unrestrained? Is it low pressure or high pressure? If it's low pressure, you can get away with fabric or rubber joints. Here's your metal joint. Here's your tie joints, hinge joints, universal gimbal. So yeah, there's a lot of logic involved in selecting any sort of these joints. Now, Caesar 2 does not select the joint for you. You will select it from a menu if you wish to use the expansion joint modeler. But basically, you have to either have a catalog in front of you or the modeler in front of you in order to enter the data. Again, I would suggest that you work closely with the manufacturer to build this properly. Now, what about this expansion joint that we wish to put in here? The piping system is quite rugged. You can take very high loads and stresses in the piping, and you don't need expansion joints. But as soon as you start to attach to equipment, now the story changes. The pipe is too stiff or too rugged for that nozzle connection. And without perhaps room for an expansion loop, that's where these expansion joints come into play. So the equipment must carry the load from both the cold and hot piping positions. And we can adjust the cold load by adding different supports to the piping system. But it's the change in load between cold to hot or installed operation that involves the thermal strain, and now the system stiffness plays a role in the operating load on the equipment. And adding flexibility is one way to reduce the load on that equipment. And an expansion joint can do that for you. Here's an example. Here's a piping system. If you've attended our training classes in the classroom environment, you might be familiar with this model. But here we have a pump at this end going over to a vessel over here. If we have to put in an expansion joint, where would we put it and why? Now, first we have to find out why we're putting in a joint in our piping system. Well, we have to carry some load on this pump. And I can run Caesar 2, and if I'm calling this node 10 down here, I can say that here's the nozzle check report for that pump nozzle, top discharge, and we see we are over 3 times the API 610 allowable limit. 2 of the loads are very, very high. Both the global MY and global MX bending moments are excessive. So here they are shown. I got this bending moment about the X and this bending moment about the Y-axis. So we're twisting the riser, and we're also pushing this elbow in the negative Z direction, causing the big MX. So what we have to do is determine which thermal strain is causing that. Is there one thermal strain or 2 thermal strains that are causing these large loads? Well, the one load, this thermal strain, as this pipe gets hot here, when this gets hot, we will twist the pipe around the Y-axis, MY, with this long moment arm here, and we'll also roll the whole riser in the negative Z direction, causing the big MX. So the thermal strain that is causing the majority of these loads down here is the growth in the Z direction. Now, if I wish to resolve this problem with an expansion joint, which joint would I use and where would I place it? So again, I want to add flexibility in Z the Z direction to take care of that thermal strain that I have on leg A. Well, I can put an untied joint on leg A, maybe a tied joint on B or C, or maybe some hinge points or maybe a swing joint on leg B. I'm going to leave the hinges to the manufacturer to discuss. Again, with hinges, there are larger rotations, and pipe stress program using F equals Kx. If you have large rotation, we cannot maintain that geometric constraint of that rotation. I'm going to focus on these 2 here, the untied joint and the tied joint. Now, if I wish to put an untied joint, I have to control the pressure thrust. So an untied joint would go on leg A because that's axial growth then of that untied joint. But then I'd have to put guides on this run, and if I put guides here, the thermal strain here on leg B would overload the nozzle about the Z-axis. So that extra hardware that I have to install in here pretty much eliminates as a feasible solution for our problem down here. If I put a tied joint in my model, I could put it on B or C. But if I put it on leg C, I'm taking advantage of the flexibility in both the Z direction and the X direction, the 2 directions perpendicular to the axis of the pipe. So I would have to say that a tied joint on leg C, right off of the pump, might be the best location for a tied expansion joint to solve both of these bending moment problems. So yeah, I'm going to go with a tied joint on the riser. In our next video, we'll take a look at how do we select the right joint from the catalog. We'll work with this system here and calculate the demand on the joint and then pick a joint from the catalog.